Okay, so the last thing we were talking about was the following. If you have two objects that are in thermal contact, uh, two objects are in thermal contact if they can exchange thermal energy. Okay? So you can exchange thermal energy via conduction. Okay? Conduction is generally when you have a solid contact. You can exchange energy via convection. Okay? Convective heat transfer is, for example, is heat transfer through the motion of fluids. Okay? So a moving fluid actually is transporting heat. So for example, in this example, the fire warms this air, which expands, which gets lighter than the surrounding cold air, and it rises up. Okay? Why does it rise up? Because its weight is less than the weight of the surrounding air. Its density is less, which rises up, so the warm air is transporting heat to you. That's convective heat transport. And then every object emits electromagnetic radiation, so you're exchanging heat via electromagnetic radiation, energy via electromagnetic radiation. Okay? Now the strength of the thermal contact might change. Okay? It will depend on the type of situation you're dealing with. Okay? We talked about conduction last time. Okay? So again, we are interested in this because, for instance, right now, heat is flowing out of this room into the environment through the walls. Okay? So the rate of heat flow, okay, is equal to the thermal conductivity of the substance through which heat is flowing, the area of cross-section, and this is the temperature difference between the two objects divided by the distance, how far apart they are. Okay? Or in this case, the length of the conducting object. All right, this is the temperature gradient. Okay, and heat flows from a higher temperature to a lower temperature. So dt by dx, if x is that direction, dt by dx is negative, and so there's the negative sign. Okay, so the rate of heat flow is the thermal conductivity times the area of cross-section times the temperature gradient, okay, negative of the temperature gradient. And again, when heat flow happens via conduction, okay, these atoms are not moving. Okay, the hotter end, they're vibrating with a greater amplitude. They bump into their neighbors, transfer some of their energy. These guys bump into their neighbors, transfer energy, and that's how energy is transferred. Okay? Yeah, we saw an example of computer heat. Okay. Again, most of you are generating 100 joules of heat per second, okay? And so is your laptop. So in a data center, in a server farm, you can have up to 10,000 computers in a room like this, and you can generate 1 megawatt of heat. That's roughly the heat generated by 1,000 homes. Okay? So you have to have very good air conditioning, heat management systems. Here's convective heat transfer. Okay, so if you wanted to heat a room with a space heater, you turn on the space heater, and what it does is it warms the surrounding air, which gets lighter than the cold air, and it rises up. And all the warm air is there in your attic, which displaces the cold air, and eventually all of the air in the room gets warm. Okay? So this is where you're sitting and watching your show. To warm this air, you have to warm the entire house's air. Yeah.
There's water in the
What?
there's water in the unit that's heating air.
Yeah, you could warm it like that, or you could burn it could be an electric heater, it could be a gas heater. Your goal is to warm the air around it. Okay. Now, the next few slides have a couple of examples of how heat is transported by nature. Okay, so near the equator, the ocean is warmed, and this warm air is transported all over the globe. Okay. And this is important for many things. This warm water moderates climates in colder countries. It carries nutrients for marine life and all that. So it's very important. So here's warm water flowing like this, and this is flowing like a river, except this is a huge river. Okay, so the Gulf Stream is typically about 100 kilometers wide. 100 kilometers is roughly half the width of Florida. It's 100 kilometers wide and 1,000 meters deep, which is a kilometer deep. Okay. A kilometer is when you're on the beach, you guys have seen those Embry-Riddle planes flying? That's a kilometer. Okay. So imagine a river as wide as half the width of Florida and flowing that way. Okay, so it's carrying a lot of warm water. So Mr. Ponce de Leon in 1512 discovered this, the de Leon, the inlet that we've named after. Apparently he was sailing this way, the winds were blowing in his favor, but the river was, this warm current was flowing at 6 miles an hour and he couldn't go anywhere. That's how it was discovered. Did you say something to him, Jeff? All right, anyway, so these warm currents are extremely important. They moderate the climate here, they carry nutrients and all that. And again, I'll let you guys read a whole bunch of this, most of it, but I'll give you a sense for this. So near here, this current is carrying 150 million cubic meters per second. 150 is 864 times 5, 7. 160 cubic meters is, imagine a cube from here to Krispy Kreme. That's the size. That much water is being carried per second. Right there, okay? The volume of Gulf Stream dwarfs all the rivers that empty into the Atlantic combined. What empty into the Atlantic? The two big rivers. What are the two big rivers that empty into the Atlantic? No, in the world. The Amazon and the Amazon. They only empty 0.6 million cubic meters. This is 250 times that. And this is not even the biggest current. So the point is, all the heat from here is redistributed globally. You get through convective heat transfer. It's absolutely amazing. Yeah. See, all the warm air is over there when you try and heat a house convectively. All right, now we'll talk about radiative heat transfer. Okay. So, what objects emit electromagnetic radiation? Everything. When will the only time you want to emit electromagnetic radiation? I'm sorry? Very good. See why I asked you to come to class? So when an object is at 0 Kelvin, it won't emit electromagnetic radiation. Okay. All right, so we saw this graph, the black body radiation graph, okay? And what this is telling you is the intensity of radiation with wavelength, okay? At this wavelength, it's emitting that, okay? And that's an object at this temperature, okay? So this is the black body radiation curve, okay? And what is the total energy emitted per second? It's the integral of this curve, the area under that curve, okay? So the area under that curve gives you the total power radiated in all wavelengths, and that is equal to this. Okay? So the total power radiated by an object, so you can calculate the power radiated by you, okay, is the emissivity, which is a property of the material. Emissivity is a number between 0 and 1, okay? It roughly reflects, if I shine radiation on you, all kinds of wavelength, if you absorb all the radiation, then your emissivity is 1. Okay? If you reflect everything, then your emissivity is 0. Okay? So if you can absorb everything, then you can radiate everything as well. Okay, that's the deal. Okay, so this is a number between 0 and 1. That's a constant. That sigma is a universal constant. What does a universal constant mean? It's the same for every object. Okay? A is the area of the object, okay? And T is the temperature. Okay. Now, you guys understand that kids have a larger surface area per body mass. So for kids, radiative heat loss is significant. Okay? As you grow older, your area to volume ratio decreases. Okay? Anyway, so that's the area of an object. Okay? And this is the temperature in kelvins. Temperature to the power 4. So that's the total energy radiated. Okay, you double the temperature, the amount of energy radiated 2 to the power of 4 is 16. Increases by a factor of 16. Yeah. What this is telling you is the following. Again, what is emitting radiation? Everything. So Jeff is emitting radiation. The walls are emitting radiation as well. Okay? So if everything was at the same temperature in this room, what would be the net loss of radiative heat? 0. Very good. Okay? So you are emitting radiation, but the surrounding at the same temperature is emitting radiation as well. You would absorb the same amount. Okay? So this is the net loss. This is your temperature. This is the surrounding temperature.
So it's the rate at which you give something is the same rate at which
That's
you
right.
absorb.
Yep. Okay, so the same flux is coming at you. Okay. Here's an interesting picture. Here's a picture taken with visible light. Okay, so of course, visible light doesn't penetrate. Visible light is not penetrating this bag, and so it's not able to reflect from your hands. But here's a picture taken with infrared camera, and infrared rays penetrate the bag, and you can take that picture. Okay, so black fabrics act as a good absorber. So black fabrics have emissivity greater than white fabrics. Okay, so in the winter, you want to wear black clothing so you can absorb sunlight and feel warm. In the summer, you wear white clothing. So this is showing you an object that is a good absorber, that is, it can absorb all kinds of wavelengths that are falling on it, is also a good emitter. An object that cannot absorb radiation, so it's reflecting them, is also a bad emitter. Yeah. These guys at Princeton University in 1965, this is a radio telescope. and they were looking for radio sources, and they found that no matter which way they pointed the telescope, they were getting a noise or static, a steady signal. Okay, so, and it bothered them, and they were talking to somebody in the hallway, and they said, oh, well, that's probably the cosmic microwave background radiation. Okay. So it was the electromagnetic radiation left over from the Big Bang, which occurred 13.8 billion years ago.
How many microphones do those have in them?
I'm sorry?
How many microphones do those have in them? Is it just like one microphone that records it, or is it like different,
I'm not sure.
they would get different signals or,
Yeah.
different frequencies?
Microphones, these are microwave radiation. Well. Anyway, so well, you're detecting a current, some kind of current. I mean,
Well, that's what I'm saying,
Yeah.
like, I just wondered if, like, how they would, is it just like one,
yeah, I don't know how
are they
that.
just looking for like one at a time, kind of like, how the telescopes take one, like, small picture at a time, and then they add it over time?
Oh,
Like a
yeah,
composite
no,
image,
no,
so
it's
that's what
not
I'm
an
saying, so-
integrated, yeah.
Yeah, that's what I'm saying, is like multiple stages of it.
Yeah, I'm not sure. All right, if you want to hear the story, I can tell you the story, but it'll take 3-4 minutes. So, all right. Okay, so here's the Big Bang, the universe. There's the universe, and it has everything in it. Now, this is a little after the Big Bang, so everything we're talking about is less than 400,000 years after the Big Bang. Okay? So let's say we are 200,000 years after the Big Bang. Okay? So these are protons and stuff, and there's all kinds of stuff, and these are photons. Now, so this is at 200,000 years. Everything is very hot, and this average photon energy is such that if an atom formed, it would knock off the atom. So you guys understand? Here's a photon. If a hydrogen atom formed here, it would hit the first hydrogen atom and ionize it. So at 200,000 years, no atoms could form.
Before
I'm sorry, this is 200,000 years after the Big Bang.
after.
As things expand, what happens? They cool down. The energy of the photon, average energy of the photon is decreasing. Eventually, you'll get to a point where you can't knock off electrons from the hydrogen atom. Atoms can form. Okay? And that happens at 380,000 years. And now atoms have formed. The energy of these photons are not high enough to knock off those ionize those hydrogen atoms. And now since they can't be absorbed or scattered, these photons travel, and the universe has become transparent. Okay? And that is the radiation that you're seeing. Okay? So that's the microwave background radiation. And the universe has kept expanding, and today the temperature of this radiation is 2.73 degree Kelvin. And that's what they detected. Okay? So that's what these guys detected. And here's the temperature. That's the temperature of this radiation, okay? That you're bathed in. And again, this radiation is like a black body radiation. The wavelength is 2 millimeters. The peak wavelength is 2 millimeters. So right now you're bathed in that radiation with a peak wavelength of with the most photons having that wavelength. Okay, so there's the temperature. Okay. Now, when it was first detected in 1965, again, that was the rough temperature they measured. And for the longest 65, so this variation was detected sometime in 2001. So for 35 years, the temperature was detected was uniform, but they were looking for this variation. See, the variation is 200 microkelvin. Okay, why is this variation important? The colder spots tell you where the universe was colder, that's where galaxies form. Okay, so if this temperature was uniform,
We would have less atoms.
I'm sorry?
We would have less atoms being created. Like,
No, all the atoms would be uniformly distributed and you wouldn't have galaxies forming and stuff. So you needed that fluctuation. Okay. And the reason it was so hard to detect was, see, this is you're detecting at 200 microkelvin variation. Your detector had to be in very cold. Otherwise, your detector itself would produce noise. So here's an instrument that's in space that has to be cold and all that. Anyway. All right. We've talked about the greenhouse effect before. Do you want to be reminded of it? You care to hear about it again? Okay, 30 seconds on a very important topic. Okay, the temperature of the Earth, the average temperature of the Earth in 1800 was 14 degrees Celsius. Today, it's roughly about 15.3 degrees Celsius. Our goal is to be under 16 degrees Celsius. What happens at 16 degrees Celsius? What?
a lot.
Like what? All of Greenland will melt, and then you can go mine, and that's why, somebody wants to buy Greenland. But anyway,
Ocean circulation gets disrupted, it gets warmer.
yep. Sea levels would rise by 7 meters. Okay, roughly twice the height of this room.
Ecosystem getting
Okay. It would displace about 1 billion people.
coral bleaching.
Huh?
Coral bleaching.
Yeah. All right, so what is warming the planet? Okay, so here's the basic. Okay, so you're getting sun energy from the sun. And if you don't want to warm this, if you're getting, let's say, 1,000 watts, then you want to radiate back 1,000 watts. If the output is equal to the input, then you won't warm up. And so that was a steady state for thousands of years. Now, here's the deal. The radiation coming from the sun, because the sun is at a higher temperature, this is visible wavelength. What we are radiating is infrared light. That's because our temperature is lower. Now, it so happens that the atmosphere has different properties to these two radiation types. And if we change the nature of the atmosphere, what do we mean by changing the nature of the atmosphere?
Change composition.
That's right. Like by dumping CO2, by changing composition, then the properties would change. Okay, so the more CO2 there is, Heather is an environmentalist. So, all right. So you dump more carbon dioxide in the atmosphere or greenhouse gases. Now it's not transparent to infrared radiation. It's still transparent to visible light. Okay. So if its properties were same to visible light and infrared light, you wouldn't have a problem. Okay. So, well, what has happened? In 1880, the level of carbon dioxide was 280 ppm. What does ppm stand for? Yeah. What does that mean?
How many parts, out of a million parts, how many parts does it make up?
So for a million atmospheric molecules, 280 were carbon dioxide. Today, it's 420 ppm. We've increased it 50%. Most of that has happened in the last 50 years. What carbon dioxide does is infrared light gets absorbed, re-emitted, it gets trapped. Yeah. I'm going to skip a whole bunch of slides. So here this shows you, okay, this shows you, so this is the infrared light being emitted. So if you didn't have any greenhouse gases, this is what would escape to space. This is what is actually escaping to space. Huh? Okay, again, we've gone from 280 parts per million to 420 parts per million today. Yeah. I'm skipping a whole bunch of stuff. So here's the average temperature of the Earth. How do you get the average temperature of the Earth? How do you get the average temperature of the Earth? What does it mean by saying that the average temperature of the Earth?
The hottest and the lowest divided.
Right, so here's roughly what you do. You break up the Earth into grids. Okay. You measure the temperature of this thing all year round, get the average for the year, do the same thing for every square, and average over that. So it's time and spatial average. Yep. The oceans are absorbing 90% of the heat that is trapped. Okay, so these are, this Wikipedia page has removed that figure for whatever reason. Okay, anyway, so here's how much heat we were trapping. The question is, okay, visible light is coming in and infrared light is going out. For every, if these two guys are equal, then you have no problem. When this is less than that, that's when you have problem. How much less is it? It's 3 watts, 3.14 watts per meter square. Here's a meter square. For every meter square of Earth, you're radiating 3.1 watts less, 14 watts less. Well, so that number doesn't mean anything, or at least it doesn't give you a perspective. Here's what that means. It means you're trapping heat at that rate, and again, that's like exploding 20 atom bombs every second. How long? All the time, and trapping the heat. So there's the current temperature. Okay, so here's a record of this. Okay, here's an interesting figure, and I've seen a plaque somewhere in St. Augustine by the beach. You guys ought to go check. Okay, so this is the coldest. So this is a glacial era. Okay, so this is temperature going back up to 500,000 years ago. Okay, so 8 degrees below this temperature, and then you have glaciers form. Where is the water for the glaciers coming from? The oceans. And the ocean level can decrease. The minimum ocean level is 120 meters below current levels. And if all the ice melts, Antarctica and Greenland and all, the oceans would rise 65 meters above the present level. And you can go to St. Augustine someplace by Matanzas Inlet and read a plaque that tells you that. Or you can, of course, take physics too, and, but it's interesting. Go find that thing. That's your homework. Yep. If all ice in Greenland melted, the sea levels would rise about 10 meters. If all the ice in Antarctica melted, okay, so sea levels would rise by about 60, 70 meters. Venus has a runaway greenhouse effect. Venus's temperature is 900 degrees Fahrenheit. And if it had 0 carbon dioxide in its atmosphere, its temperature would be 0 degrees Fahrenheit. Yeah. All right, guys. So